Hi everybody, my name is Nicola Antonelli. This is my reporting video of the project. First of all, I will quickly introduce this framework, the SBM IGA framework, that is combined by the shifted boundary method, which is an embedded method that does not try to integrate the CAD cells, but instead it considers a shifted or surrogate boundary, and it imposes some modified boundary condition on this shifted or surrogate boundary using a Taylor expansion. Moreover, we'll use IGA, isogenometric analysis. Why? Because it's easy to go higher order, we can have higher continuity, sometimes it's very useful, and we can use textile geometry when we import NURBS. Advantages, of course, as all embedding methods, the boundary are mesh independent. We can have optimal convergence for the Dirichlet. For Neumann, the things are a bit more tricky, but we can say we can achieve at least suboptimal convergence of order P. At the end of the simulation, we can reverse the Taylor expansion and compute the solution at the true location. We don't suffer on the so-called small cut cell instability, very common in the majority of embedded methods. It's easy to extend into the dimension, and actually we will see at the end that we did it, and it's already available in an open source software, which is Katos Multiphysics. The results of this framework has been described in this paper that has already 1 year. I invite you to go and read it if you are interested. In this video, I will explain a bit the extension of that framework to Stokes fluid. We have already done it for Navier-Stokes, transient Navier-Stokes, but here the focus is on another slightly different topic. So we taken the simplest case, so Stokes fluid. We kept the constitutive law general in order to also simulate non-Newtonian fluids. We wanted equal order discretization, so we needed a stabilization, and we have chosen the variational multiscale. I left here some references. And finally, want to implement everything in the same SBM IGA framework I have explained you before. We can start from a Newtonian case. We have taken a smooth solution. We computed the forcing we need for this Stokes problem, and we can see that we have optimal convergence for both velocity and pressure, P1, P2, P3, optimal convergence. Okay, very nice. What about non-Newtonian fluids? Non-Newtonian fluids, we know they behave differently depending on the stress in general. They depend on a constitutive law that may be simple or more difficult, but they have change of material properties. They can have a sharp transition, so actually in general they are very difficult to simulate. Our hope was, okay, we use higher order basis function and maybe they work better than linear finite element because maybe they can represent better sharp transitions. This is our hope. Let's see. So to do this, we have taken the Bingham fluid, Bingham constitutive model, that basically is a model like I imagine it as the toothpaste model, because when the stresses are below the yield stress, the fluid behave like a solid in the sense that it can just translate or stay there. While where the stresses they go above the yield stress, the fluid start to behave like a Newtonian fluid, and that's why there is that linear behavior after the yield stress is passed. Actually, we will use a regularized Bingham model in order to don't have very sharp transitions that are very difficult to simulate. But still, it's a strong transition and a quick change of material properties, as we will see later. So to start, we have taken the same smooth solution as before. We have computed the forcing such that we can get this solution with that constitutive model. It's a technique just to check if, at least for a smooth solution, IGA is working well. And actually, it is. So this is the solution. We also have insert embedded circle using the SBM also to check how the shifted boundary method behaves with non-Newtonian fluids. And actually, in both cases, with the immersed circle on the right and without any embedded circle, we have optimal convergence. We can see from this, this is the velocity convergence. In both cases, we have similar. Of course, with the SBM, all the curves are shifted a bit above because we are introducing an approximation, imposing the boundary condition on the surrogate boundary, and the same for the pressure. But still, optimal convergence is obtained. Very nice. So what we can see now is that with higher order basis functions, smooth solution seems to work very well. But what about more physical solution? What do I mean by physical? For instance, not super physical, but still more physical than before. We can take a Poiseuille flow of a Bingham fluid. This is basically a Bingham channel, is a Poiseuille flow. We put some Bingham fluid inside, and actually an analytical solution is available, and it is simply a piecewise quadratic solution. We can see the profile on this picture. We have two benches of parabola on top and close to the two walls, because there the stresses are higher, and therefore the Bingham behaves like a Newtonian fluid, so a parabola, branch of parabola. In the middle, we have the unyielded zone where the fluid behaves like a solid. So we have just transition with no deformation. Okay, so piecewise quadratic solution, we expect to, okay, I was expecting, okay, I can use P2 IGA basis function. I will get immediately, no matter which mesh the analytical solution. This is simply a piecewise solution everywhere. So it's constant in the middle and parabola close to the walls. But actually, what we obtain is that, okay, P1 converge with second order convergence as expected, but P2, P3, P4 up to P6, at most, we have obtained second order convergence, not more than second order. Why? Why is this? We have found the answer to this question in the literature because the convergence rate estimate has a limit that depends on the higher finite derivative of the exact solution in the L2 norm. And in our case, the solution, it looked very smooth, but actually it was piecewise quadratic, as I said, and there was a discontinuity in the second derivatives that this leads to a singular point in the third derivative of our exact solution. Therefore, the third derivative is not square integrable, and therefore the limit of this estimate was actually 2. That's why we got at most second order convergence. So this was actually expected from the literature. And we can see here the absolute error, and we can see some Gibbs-like effects close to the two lines, 2 points where we have the change of material properties. We can also go to a more complex benchmark, which is entry flow of Bingham plastic in sudden expansion, which this is the geometry, and on the right you can see the benchmark solution from the literature. In black we see the unyielded zone, solid-like regions, and in white the yielded zone where the fluid behaves like a Newtonian fluids. And our solution with P1 with a very fine mesh is not easy to get these results. It is in agreement, perfect agreement with the reference solution, very nice. But what we are interested in this talk is how higher order basis function perform. And the answer is P1. And to answer this question, we have taken two different meshes. First column coarse mesh, second columns a more fine mesh. First row P1, we can see that the coarse mesh a bit capture the behavior of the of the physics, but not perfectly, especially in the center of the channel, where you need very fine mesh to get the full contour of the yielded unyielded regions. But the fine mesh, it captures it quite well already. If we go to P2, similar results, slightly worse than P1, using the same mesh. And P3 is the worst between the three. And even the fine one cannot capture the behavior at all in the center of the domain. So this is a very bad news. This was unexpected from our side. Um, why is this? Probably because in this case, some crosstalk effects, but in general, the solution, the analytical solution, was not available. But for sure, it has some sharp change of material properties due to the Bingham constitutive law. And this, the exact solution probably has some discontinuity in the second, in the third derivatives. We don't know because it's not available. And this limit the convergence. And actually, it can make it even worse than P1, uh, probably for some crosstalk effects of the larger support of the basis function in IGA. So to answer the questions, IGA probably is very good for smooth solution, even in fluid dynamics, even for non-internal fluids, but when you know that the solution is smooth. So while for more physical solution, so when you don't know, or your constitutive model can introduce some kind of discontinuity in the exact solution. Even the Bingham problem, it looked very smooth, but actually, if you investigate, it's not smooth at all. Already, the third derivative has a singular point. Probably IGA is not the best way to simulate this kind of fluids. You can still do some local refinement close to the change of material properties. This for sure would help. Or basis order reduction in the area where you know that you don't have that much continuity, and probably use P1 in that area will a bit solve the problem. While in the area where you know that you have a smooth solution, maybe far from the change of material properties, it makes sense to increase the polynomial order and use IGA. This is the result of this second paper published last month. So if you are curious or interested, please look for this paper. Finally, very quick, some potentiality of the SBMIJ framework in three dimension for a simple Poisson problem with Dirichlet boundary conditions. We can see that we have optimal convergence for Dirichlet, suboptimal for Neumann boundary condition, but the real potentiality is that we can simulate very complex geometries, even in 3D, something that for the majority of embedding methods is not easily extensible to 3D. But here you can see that it's quite robust, and we can simulate the 3D Stanford-Bunny with optimal convergence also in this case. We can even simulate even more complex shapes like this mechanical component full of details. And of course, if we use a mesh that is two cores, we will lose some details of the geometry, but as we have found, we recover all those details. And the real advantage of this is that for large deformation, or if we have a moving body, we don't have to remesh every time. We have just to recompute the surrogate boundary, the surrogate surface in this case, which is a very easy and cheap procedure. This is all. Thank you very much for your attention. Bye.